Good morning, mathematicians. So, I'd actually bought an HDMI converter to use my better camera, but it's not working. I wonder what the issue is. Could be the HDMI cable, could be the camera, could be the $20 piece of junk I bought on Amazon. I don't know. But we will have to go ahead computing spectral sequences without, my face in absolute crystal clear detail. And I know you're pretty sad about it, but we'll just start doing some math and you'll forget all about it. Okay. Also, I've got my new pour over in this container here, and it's still kind of weak this morning. I did a better job with the grinds. I think maybe my water bean ratio is off. That's probably the next thing to address. Okay. So, E infinity is the associated graded with respect to some filtration of some cohomology. That is, there is a filtration. I set -1 to be 0. Okay. Sure. We've got these short exact sequences. Starting from I equals 0, the dream would be to work our way up to solving the group extension problems, and thus work out the filtration. Right. Go see my videos on group cohomology. There are nice cases, such as when we are working over a field, if we otherwise only have free modules and trivial extensions. Yep. In the present calculation, we can sidestep this problem using our earlier calculation of SUN, because there's a split short exact sequence here. Good morning, Arad. Where... Notably, this is different from our earlier embedding U1 into U2. Hence, as a manifold, we have this. Sure. Okay. And now recalling that U1 is that, and SUN is that, it follows from the Künith formula that we have that. Okay. So we got the U2 is a symmetric algebra, which is what we were originally trying to prove. Returning to the additive extension problem, we see that the Z2 and Z with total degree 3 on the E2 page should assemble to give Z. We can now work backwards from the answer to deduce that the filtration must have been that. Okay. Sure. Finally, we have the multiplicative extension problems. There are also situations when we can determine the cohomology groups, but not the ring structure. Just as we factored the Hopf fibration, in step 8, we can factor the quaternionic Hopf fibration. By taking quotients to obtain a fibration here. S2, yeah, okay. Wait. S4, sure. Why is S3? Oh, and I guess because S3 is trivial fundamental group. If you quotient out by a circle, you're like collapsing a circle, but that shouldn't do anything. Same with S7? No, I don't understand. I don't understand at all, actually. Wait, CP3. Is CP3 S7? Okay. Anyways, we already know the cohomology of each space, but suppose we wanted to recalculate this using our new fibration. Once we have filled in the groups on the E2 page, we observe that the spectral sequence collapses at E2 for degree reasons. What can we say about the ring structure? If we let this be generated by X and this be generated by A, then we get this. And after that, we are stuck at the following picture. That was like me yesterday. In fact, we know from step 3 that we should have that, but there's no way to deduce this from the spectral sequence alone. Okay. Property 4. The ring structure on the E infinity page is the associated graded of the ring structure on cohomology. Okay. Note that by property 3, a map here should correspond to a map of the associated gradeds. Property 4 then says that the multiplication on the E infinity page is given by quotient maps induced by the multiplication there, which is in turn induced by the cut product. Taking the associated graded in this way can kill some of the multiplications, so it is non-trivial to recover the graded ring structure. This is a multiplicative extension problem. Okay, and we're done. And we're down. Shallow staff? Shallow staff? Were you trying to say shallow stuff? I don't know what you're trying to say. Sorry. Let me move my stupid camera setup. I gotta figure out what's going wrong with that thing. Okay. Where are we off to now? Now we're gonna go to Aluffi. And we're gonna read about exact couples from Aluffi. Now that we've graduated from our first document. Spectral sequences. Boom. Boom. We mentioned in 8.3. Okay. So, triangles. So, we suppose we're in some abelian category, and we suppose that we have some triangle of morphisms. E, A, Let this be an exact triangle. Okay, there's a footnote. What does that little footnote say? Oh, is it at the back of the book or something? What does it mean? I guess it just means it's exact at each position. Each one of these maps is exact. Surely that's what it means, right? And so we're going to let D from E to E be the composition gamma beta. And since beta gamma is 0, the differential is 0. So we can take homology. Your favorite perspective on spectral sequences is by unrolled exact couples, though unfortunately they don't seem to be so common outside homotopy theory. Interesting. You got a blog post about that or what? Well, I'm going to need to digest these ordinary exact triangles first before I worry about unrolling anything. Okay, so then E prime. E prime is just the homology with respect to those. And if we let A prime be the image of alpha, then we claim that we get a new triple. All needed verifications are straightforward. Okay, yeah, let's just check exactness at one of these places. So, so we'll have A prime, E prime, A prime. Which one's this? This is gamma prime. This is beta prime. This is alpha prime. Okay, let's check. No, wait, did I? No, I put them in the wrong order, didn't I? Sorry. So let's check exactness at A prime. Let's check that the image of gamma prime is the kernel of alpha prime. And I guess I'll just trust that it's a complex. So we'll just suppose that let y be in the kernel of alpha prime. Is there any course in the PhD program to teach LaTeX usage inside average US math department? No. There really isn't any need. I don't know what you would do a whole course on. You know, sometimes like people might run a tutorial or a workshop or something, but there definitely isn't enough content to fill a whole course. And I mean, most people seem to be able to learn on their own just fine, especially nowadays, you know, with YouTube and Stack Exchange. I mean, all of my preambles, like, I don't know what half the stuff does in there. I just copy paste stuff that worked for other people from Stack Exchange. So, yeah. Okay. So, let's see. So what does that mean? Well, this is just the restriction. Alpha prime was just the restriction of alpha to A. And so this means that y is in the kernel of alpha, which means that it's in the image of gamma. And so we can let x be in E such that gamma prime maps to, or sorry, that gamma maps to y. There's only one way to learn LaTeX, and it's the day your first mandatory typeset homework is due. Yeah. You remember your first course where they said, yeah, you have to use LaTeX, but we'll let this handwritten submission slide for the first one. I regret, well, actually, yeah, when I taught the Galois theory course, I was actually, the other instructor taught for the first month and then went on paternity leave. And so, unfortunately, he set the precedent for a bunch of things, including he didn't demand LaTeX, which I definitely would have if I had been in charge from the beginning. But what can you do? You lose some, you lose some. Okay, and then that does it because y prime, because now we can just take the class of x, and y prime maps the class of x to, gamma prime maps the class of x to gamma, which is y, which is what we wanted. Nice. Okay. Great. So the new triangle, is again exact. Oh, it's unfortunate that the style of this PDF does that thing where it doesn't let you to cross pages. It just instantly hops, which is going to be super annoying for us. Your professor said you may never think about elliptic curves again, but you'll use LaTeX for the rest of your life. Yeah. Which possibly both are wrong. Well, yeah. I don't like imagining any of my students are non-mathematicians. A lot of math students in their 5th semester are using Word for notes and assignments. Wow. They would receive the death penalty in my dictatorship utopia. Click the page icon in the bottom right. Oh, this? And allow scrolling. Oh, enable scrolling. Arad, you're a genius. Goddamn genius. That is why I pay you the big bucks. In my head, anyways. I pay you the big imaginary dollars. So, do I know about derived functors? Well, yes. Most certainly. I know about them. I use them all the time. It would be very strange to be at this point reading about spectral sequences. In fact, one thing I would like to understand is that there's the paid in blue for their username. Yeah. One thing I would like to understand is there's a spectral sequence argument that allows you to prove that the composition of two right derived functors is the right derived functor of their composition. So I think that's a classic basic thing that you can prove with spectral sequences. You saw the Y of cohomology video and would have talked about derived functors in some sense there. Maybe that's good for a follow-up video. Is that the Grothendieck spectral sequence? I don't know. Yeah. my yeah, that's maybe for another video. That's maybe for a follow-up. I want to try and make cohomology not scary for people. The datum of an exact triangle as above is called an exact couple, which we find confusing since the triangle has 3 vertices. Yeah, by the way, I loved Alt J's first album. Maybe some of you are too young to even know it. That's not true, but in their song Tessellate, it always confused me that they described a triangle as 3 points where 2 lines meet. Wasn't it 3 lines? Triangles of 3 vertices. Well, maybe there's other geometries where they don't. What about degenerate triangles? Okay. Anywho. But it is true that only 2 objects are involved here. The new exact triangle is the derived couple, which we find even more confusing since there's no derived category or functor in sight. It makes sense to me, though. Of course, we can turn the crank at will and get derived couple after derived couple. Yeah. Beta I+1 is obtained by rewinding the morphism. Yeah, how are they defined? Interesting. Yeah. What is this seminar usually like for the advanced class? Does the professor discuss with student equally? I mean, this completely depends on the professor. Yeah, so I don't know if there is any notion of what it's usually like. I think it just varies wildly from university to university and professor to professor. Yeah. Lots of seminars are run very differently, so not sure there's a good answer for you there. As a math person, you can't support all this couple talk. When they talking about exact singles, call me. Yeah. Yeah, I've been thinking, I'm like, oh yeah, definitely got some ammo for some Valentine's Day one-liners here. Hey girl, you into spectral sequences? Because I think we would make an exact couple. Exact singles in your open neighborhood. My neighborhood's clopin all the time. Where's the link? Yeah, thus one exact triangle produces a whole sequence of triangles, and in particular a sequence of objects endowed with a differential. Boom, nice. Definition 1 from Aluffi: a spectral sequence is a sequence of objects and morphisms in an abelian category such that that is true. Thus, exact couples are a way to produce spectral sequences. No? Okay, carry on. Yeah. There is a sense in which we can turn the crank infinitely many times. In fact, this can be done to any spectral sequence. Okay. Let's write down some definitions. So, boom. Z1 is E1, B1 is 0. And is E1 just our E? Is E1 just our E? Where did we define things here? Yeah, E1 is just E. Although, unironically, you have had talking about math work as Riz a few times. If you can talk about something passionately and make it meaningful, people like that. Yeah, I would say that's true. I would say that's true. Also, where's this? There's an SMBC comic about this. Where is it? Comics tagged with mathematics? Maybe it's going to be way too many. Although, I wonder, do I have this one saved on my... I might have this one saved on my... It might be somewhere... It might be on my Google page, actually. Let's see. Ooh, that's blurry. I gotta fix that. Oh yeah, here it is. Here it is. Yeah. Wrong approach. Kids, math is fun. It's like a safari to find the value of x. Right approach. If you're a mathematician, there are about 10 people on earth who understand what you do, and none of them have the power to fire you. You have no set hours, everyone respects you, and you work about 5/8 of the year. If you go to a bar and tell a woman you are employed for your intellect alone, she'll probably sleep with you. But hey, feel free not to do your homework. It's not my problem. The key is to just use lots of technical language and scoff whenever they don't understand something. Yeah. Get on the math nagging approach. Okay. So then E1 is the quotient. And assume we've defined these in such a way that EI is isomorphic to their quotient. Then if we define zi plus 1 bar to be the kernel of di and bi plus 1 bar to be the image of di, then then okay, define these to be the corresponding subjects of zi. Why is that possible? Why is that possible? focus on GSM textbooks? Sorry, is that a request? Are you requesting me to read GSM textbooks? Right. Wait a second. We haven't... Okay, right. ZI is defined. Right. ZI is defined. And ZI is defined... it's in order. And ZI is defined in such a way that this is true. And... Right. DI... I mean, EI plus 1 is supposed to be the quotient of the kernel of DI plus 1 mod the image of DI. So... So what? So what? Is the corresponding subobjects of ZI. I don't know why I'm finding this so confusing. Let me just do the very next step from here. So, okay. So, what was it? E1. Sorry, Z1 is E1 is E. Z1 is E1 is E. And B1 is 0. Okay. Now, I'm trying to come up with a subobject of Z1. So, what do I have? I have E2, by definition, is the kernel of D2 mod the image of D1. You should probably give up and become a baker. That is oddly bitter, but no one knows why. Maybe I do have plans with a friend of mine to open a bakery in Bogota. Are you saying he's not cooking? Well, I can put this in a short exact sequence here. Right. Wait a second. No, what am I doing? No, I mean, this is just a definition. Wait, what is D2? What am I saying? No, it's the kernel of DI modded. Wait, the image of DI? What am I? Now I've gotten myself confused. Right, those are both DI. Right, those are both DI. Because it lands in the same thing. Right, so sorry, this is kernel of D1, mod D1. Right. And so... You used to call a 4-term exact sequence a pretty short exact sequence. Yeah, you could make pretty short exact sequences be a thing. That sounds cooler than kernel co-kernel sequence. Yeah. Okay, so this makes more sense. Short-ish exact sequence, yeah. So, what am I? Why is my brain not working here? I mean, E2 is just this quotient, right? Image of D1, kernel of D1, and then the quotient is here. And I want to express this in terms of Z1. I mean, Z1 in this case is just E1. And this already is a subobject. This already is a subobject of E1. So am I just taking Z2 to be the kernel of D1? In this first step? And then I would take B2 to be the image of D1? Right? I mean, that seems simple. Used to be an exact sequence until you took an additive functor to the knee. Yeah, so that should work. I guess maybe the next step is where things get trickier. So now right. Right. So now I'm going to go to E3, which is the kernel of D2 mod the image of D2. And now I see, in this case, the kernel of D2 is really a subobject. The kernel is a subobject of the kernel of D1 mod the kernel of mod the image. Right, so I should be able to lift this. I should be able to lift this to a subobject of D1. Right, there exists some lift of this. I can write the kernel as some. I can write the kernel of this as this, where Z2 is a subobject of here. Right, I see. It also says the subobjects. Is that really well defined? Could I not take more than one lift? What am I trying to cook right now? I'm trying to come up with ZI plus 1 and BI plus 1. But then he's saying the corresponding subobjects of ZI. And why would that be well defined? This is third isomorphism theorem. Bijection between the subobject lattice. Right. Okay, so it really is the... Okay. Then realizing this, where are all these footnotes? Oh, they're there. Okay. Then we get these chains. B infinity is the union. Z infinity is the intersection. Is that union really in the intersection? Yeah, I guess all the B's are in all the Z's, so. Sure. This is the limit of the spectral sequence. It is common to say that the spectral sequence abuts to E infinity. By definition, if the differentials are eventually 0, then those stabilize at the rth page. You cannot tell me what the first two isomorphism theorems are? What? How could you not? But you're pretty sure you only need to remember the third? What? No, that's insane. That was totally bass-ackwards. Aboots. It aboots. That'd be the Canadian way to say it. The reader will verify. Don't you tell me what I will or will not do. That if the spectral sequence arises from an exact couple, then this is true. God, why is that true? Yeah, I mean, the third isomorphism theorem is a consequence of the first isomorphism theorem. So, it is inferior. Well, you're sure you know them, but what is 1 or 2 or whatever? Who knows? You can say that the second should be the third and the third should be the second, but the first can stay first. Yeah. Sure, I agree. Okay. I guess we need to prove this. I guess we should say why this is true. So, we want to show that gamma inverse. What is gamma here? Which gamma is this? Is the intersection of all the images of all the alphas. We want to prove that this is Z infinity. Well, Z infinity is the intersection of all the ZIs. Okay. Boot. What's the claim here? That this should be the case if it's a spectral sequence arising from the exact couple. It's a fun exercise to prove the third isomorphism theorem using the snake lemma. Oh, yeah. What are we trying to do here? Maybe, what am I trying to do here? I've got a spectral sequence defined by exact couples. I see. It's more likely your deep personality flaws. I mean, couldn't you say that being the alpha is the deep personality flaw? Could one not say that? Would one be right? So, right, E infinity is this quotient. Maybe we want to use that fact. Okay. Whatever, let's try to prove it, I guess. So, suppose X is in gamma inverse of the intersection of all the alphas. So then we know that gamma X, the inverse image of that. So gamma X is in the intersection of all the alphas. And that implies what? Well, that means for each R, we can choose. Well, it's in the intersection of all of them. So actually, that means we can choose a Z, I don't know, which is in the image of here for all R, such that gamma X is alpha R Z. And what am I trying to do? I'm trying to prove that X is in every Zi. Out of coffee, damn. I'm trying to prove that X is in every Zi. Well, how did we construct the Zi's? I mean, the Zi... I feel like it's got to be right in front of me. I mean, by our choice, we chose... Each Zi is chosen to make this true. That's basically all we know about the Zi. It's nice at this point to think of Zi as chains whose boundaries contain in the ith previous filtration step, and Bi is chains which are boundaries of something in the next ith filtration step. Sure. Okay. And I'm not quite sure I see it. Zi. Blah, 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 blah. I mean, I feel like it's right here because of how we choose these. I'm just not sure the right way to articulate it. Maybe I'll gain some insight if I go in the opposite direction for a moment. It's also nice to work with one's hands and play a part in feeding your community nutritious breads. Yes it is. All right. Yes it is. Or sorry, Leo. I was looking at the wrong username as I said that, but indeed it is. Okay, hang on. What if instead, let's take X, which is in the intersection of all the Zi's. which is in the intersection of all the zi's. And then what? That means I want to cook up something in the intersection of all those images that maps to X. Okay, well, if I'm in all the Z's, what do I know? I know that somehow well, if I'm in all the Z's, what does that mean? No, I don't know. I'm going to come back to this later. Wait, what if I try the statement about the betas? What if I try the statement about the betas? Will that make more sense to me? So we want to show that beta is the union of all the kernels, which is the union of all the BIs. No, I don't think this will make sense to me. I mean, suppose Y is in here, so then I can choose X, which is in every single kernel, such that beta X is Y. Maybe this one does make more sense because so it's in, well, X is in the kernel of some fixed, say some fixed R. I can choose an X in one of these kernels. And what does that mean? Yeah, I guess if we think no, wait. The kernels? Well, if X is in the kernel of that, then 0 is alpha R of X. And alpha went from where to where? Alpha R goes from one of the A's to one of the A's. Alpha R goes from A to A. But that means if you're in the kernel of alpha R, and this is an exact couple, then that means that you're in the image. That means that you're in the image of gamma R. So that means that there is a Z in ER such that gamma R Z is X. Where am I going? I'm trying to say this is in the union of the BIs. But I mean, what is z? Z is really something. Z is really a z naught. Z is really a z naught plus an image. What is gamma r? Gamma r is defined, I mean, it'll eat the equivalence class of some element. How is it defined? And just sends it gamma of, well, r minus 1, I guess the previous step here. Take on what homomorphism means? What do you mean? A homomorphism of what? Of groups? It just means this. For all elements in the group, phi is a homomorphism if phi of A times B is phi times A times phi times B. There's a homomorphism of groups. There's homomorphisms of lots of other things. Take it on and defeat it, yeah. What does this mean? What am I even trying to prove? What do I have anything to prove to anyone? I don't have anything to prove to you. Where am I here? I'm trying to show that this is in one of the BIs. Well, the BIs are defined in such a way, I want that to be the image of some D map, right? And how is my differential defined? My differential DI is I mean, it should be how did we define it up here? So DI is the composition of beta I. Maybe I should put it upstairs. Doesn't matter. DI is a composition of beta I and gamma I. And I know something about these now. I mean, DR for the sequence objects? I'm sorry, math, but I have no idea what you're talking about. I mean, in this case, we're just working in an arbitrary abelian category. So the morphisms are whatever the morphisms are. But if you like, you could think of them as modules. That's a module homomorphism. And what was this whole story? I started with this y. I was trying to show that this y ends up somewhere. Hello, Fimnal. I was trying to show that this y shows up somewhere. And y is beta x. Y is beta x. And now I know that x is gamma of something. So y is beta rx. And x is beta r gamma r nice of some z. Well, really, I should call it z naught. Nice. Okay. So I think that kind of does it. That does this in one. This partly does it. Because now y is in the image of this differential. So it's in, it's got to be in one of these BRs. Oh, I still feel a little bit weird about the way that, yes, of course, we're applying this bijection, the sublattice bijection through the third isomorphism theorem. And I totally believe that, yeah, saying it's in the differential here, of course it's going to lift to something in the differential there, but it still feels a little weird. But sure, okay. I mean, at least I'm happy enough. I'm happy enough just by saying y is in dr, and so that implies that y is in br. It's got to be, right? Yeah. Okay. I think that's it. We've been streaming for over an hour, I think. So I think that's going to do it for today. Yeah. Tomorrow will come full circle, I think. We'll turn the crank until our spectral sequence converges. That is what we'll do tomorrow. I'll see you all then.